One grows in the sun and the other underground, yet both end up in your candy bar. It's not magic, but it might as well be. So how do both sugarcane and sugar beets take different paths to produce the same sweet result? Did you know that around 40% of the sugar in US comes from sugarcane? This tall, tropical grass is cultivated in warmer and humid climates like Florida, Louisiana, and Texas. It all kicks off in the fields, where the farmers get the soil just right, loose, well-drained, and ready to go. Then they drop in the sugarcane cuttings, tucking them into furrows and covering them up. These cuttings mature over the course of 8 to 22 months, relying on lots of water, sufficient sunlight, fertilizer, and pest control. This is the crucial phase when the sugar builds up in the stalks, storing increasing amounts of sucrose, which is the sweet, juicy goodness we use in processing ahead. When the sucrose content in these stalks is at its peak, it's time for harvesting. Harvesting can be done in two ways: the traditional methods with knives or machetes, or the high-tech mechanical route. In the US, mechanical harvesters do the heavy lifting, carefully cutting the canes close to the ground and leaving a short stubble for regrowth. Then the stalks are chopped into smaller billets, making them easier to transport and process at the mill. The billets are loaded onto trucks specially designed to carry large quantities of sugarcane. These loaded vehicles then transport the cane to the mill, often within a few hours of harvesting, to prevent sugar loss and degradation. Upon arrival at the mill, things move fast. The billets are weighed, sampled, and given a good wash to get rid of all the dirt and debris. The cleaned canes are then fed into heavy roller mills, which are large, industrial-sized cylinders that crush the sugar cane and release its juice. These rollers apply pressure as the cane passes through them, which squeezes out the sugary juice while leaving behind the fibrous, pulpy residue called bagasse. Instead of wasting this bagasse, it is repurposed to generate energy for the mill, helping power the entire sugar production process. As the canes are shredded in the rollers, water is often sprayed to extract as much juice as possible. This extracted juice still contains impurities like mud, waxes, and fibers, which is why it undergoes clarification. The raw juice is first treated with lime or calcium hydroxide, and then heated in juice heaters at a temperature of around 212 to 221 degrees Fahrenheit. This hot limed juice then enters a large settling tank where the impurities settle at the bottom, leaving a clearer liquid to flow off the top. The impurities, often called mud, are then filtered to recover any sugar that's still trapped in, while the solid residue is used as fertilizer in the fields. The clarified juice, still diluted, is thickened in a series of multiple effect evaporators. These machines boil off the water under low pressure until the juice turns into a sticky syrup. Now we've got the sticky syrup, but to turn this liquid gold into actual crystals, we need vacuum pans. These are special enclosed vessels that boils the syrup at a lower temperature by creating a vacuum. Under carefully controlled conditions of the vacuum, fine sugar seed crystals are added to the syrup. As the syrup boils in the pan, the water continues to evaporate and sugar crystals start to form, growing bigger and bigger until they reach the perfect size. At this stage, we've got this thick, slushy mix of crystals and the remaining liquid called massicute. To separate them, the mixture is transferred to a centrifuge where it is spun around at high speed of around 1,000 to 1,800 RPM, and the immense force pushes the liquid molasses away, leaving behind solid sugar crystals. These crystals are given a quick rinse with a little water to make sure they're extra clean. Finally, even though they're mostly sugar, these raw crystals are still a bit damp. So we send them through rotary dryers where a gentle tumble with hot air removes that last bit of moisture. This process prevents them from clumping together and ensures they are ready to be stored or sent to the sugar refinery. After we've gotten that golden brown raw sugar, it is time to convert it into the sparkling white sugar we all love at a sugar refinery. First, the sugar is mixed with a warm syrup to loosen the molasses coating on the crystal. Then it gets spun in the centrifuges again. This washes away excess molasses coating. This sugary liquid goes through intense filtration and decolorization, often using activated carbon. Finally, this perfect clear liquid is recrystallized in vacuum pans, forming pure white sugar crystals. The white crystals are separated in centrifuges one last time, dried with warm air and then sorted by size, where it is fine granulated sugar, superfine or powdered. After all these intricate steps, this dazzling white sugar is ready to be packaged and shipped out. ready to sweeten your life. Now that we've seen how sugarcane is transformed into sugar, let's take a look at the other primary source of sweetness, the sugar beet. Grown in cooler, temperate climates like the Midwest and Western United States, sugar beets are rooted vegetables that, much like sugarcane, are packed with sucrose. Unlike sugarcane, which is grown from cuttings, sugar beets come from seeds. Farmer plants these seeds in the spring, typically from late March through April, in a well-drained, fertile soil. For sugar production, they are harvested in the autumn, typically late September and October, when the sugar content is at its peak. Specialized harvesters are used to efficiently lift the beets from the ground, remove their tops, and clean off excess soil. When harvested, the sugar beet root contains 12 to 20% sugar. The rest of the crop is made up of water, 75%, and pulp, 5%. This means that the beets must undergo processing to extract the sugar. Interestingly, while both sugarcane and sugar beets produce the same sugar, the two types of sugar have subtle differences in flavor. Beet sugar tends to be more neutral, while cane sugar has a slight flavor variation due to its molasses content. Once harvested, the beets are quickly loaded onto large trucks and transported to the nearby processing factories because their sugar content degrades quickly. At the sugar mill, the beets are initially washed thoroughly to remove soil and stones. They are then sliced into thin strips called cassettes, which increases their surface area, making them efficient for sugar extraction. These cassettes are then fed into a large vessel called a diffuser. Imagine a giant warm bath, typically humming at over 167 degrees Fahrenheit. The magic of diffusion unfolds. Hot water gently dissolves the sucrose from the beets into a raw sugar juice. The remaining beet pulp, which is low in sugar, is pressed to remove excess water and is a valuable byproduct, often used as animal feed. Now the raw beet juice emerges, looking a bit murky as it still contains various non-sugar impurities. It undergoes a purification process called carbonation, where lime, calcium hydroxide, together with carbon dioxide is added to the juice. The lime reacts with the impurities, causing them to precipitate, forming solid calcium carbonate particles that can't dissolve in the liquid. Then these purified liquids are sent through powerful filter presses that act as huge sieves. These filter presses remove the trapped impurities, resulting in a clearer, lighter-colored juice. This filtration is a secret weapon that allows beet sugar to achieve its natural white brilliance without further refining. Similar to sugarcane processing, the purified beet juice is then concentrated in evaporators to create a thick syrup. From this syrup, the final white granulated sugar is produced. This is where the paths of sugarcane and sugar beet processing truly diverge to create the ultimate final product, sugar. Unlike sugarcane, which produces a raw brown sugar after the evaporation process that requires further refining to become the sparkly white sugar we commonly use, the beets process directly produces white granulated sugar. This notable difference is due to the rigorous purification steps the beet juice undergoes before crystallization. The thick, sticky syrup is transferred to vacuum pans where, with the help of seed crystals and controlled conditions, the sugar crystallizes. As the beet syrup doesn't have a significant molasses coating or impurities that give raw cane its brown color, the separation of sugar crystals and remaining liquid using a centrifuge is sufficient to get that inherently white sugar. These pure white sugar crystals are then dried with hot air, cooled, and screened to separate it by crystal size. Here's a fun fact. After the centrifuge spins out the sugar, it leaves behind molasses, a dark, sticky liquid. This molasses isn't wasted, though. It's often turned into syrup, used as animal feed, or even fermented to make rum and other alcoholic beverages. Once the sugar is fully processed, whether from sugarcane mills or beet factories, it's finally time for packaging. This is a highly automated operation, designed to ensure quality that meets consumer and industrial standards. Automated machineries fill everything from small single-serve packets to large industrial sacks. The bags are sealed and inspected for quality control. Finally, they're boxed, stacked by robots onto pallets, and shipped out nationwide. From humble stalks and roots to the sparkling crystals in your coffee, we've witnessed a fascinating journey that transforms simple plants into world's most essential ingredients. If you enjoyed this breakdown, like and subscribe for more and turn on notifications so you don't miss the next one. In modern agriculture, nothing rivals scale, power, and efficiency. Meet the New Holland CR11, the world's largest and most powerful combine harvester. Born from decades of innovation and cutting-edge engineering, it can rethink entire harvest seasons. Today, we'll go inside the factory, into the cab, and through the field to discover how this machine is built, what makes it groundbreaking, and why farms worldwide are embracing its extraordinary capabilities. Grab your seat. Let's uncover the making of a harvesting legend. Before steel is cut or bolts are tightened, the combine is born as a digital twin, a 3D simulation created by engineers at CNH Industrial. The CR11 is designed for mega farms harvesting thousands of acres at a time. Its goals: harvest up to 135 tons per hour, store 20,000 liters of grain, and operate 24/7 with minimal downtime. Engineers optimize every subsystem: cutting, threshing, separating, cleaning, and grain handling, using fluid dynamics and stress simulations. The combine must withstand mud, dust, vibration, and extreme heat. Even the cab ergonomics are mapped out digitally to maximize operator comfort over 16-hour shifts. The CR11 is designed around a twin axial rotor system, massive grain tanks, and a 775 horsepower Cursor 16 engine that meets the strictest emission standards. Every component, from rotor angle to tire tread, is designed to handle colossal workloads. Once the blueprints are locked in, production begins with steel fabrication. Thick, high-strength steel plates are plasma cut into structural shapes and welded by industrial robots to form the main chassis. This skeletal frame is the spine of the machine. It supports the cab, engine, fuel tanks, axles, and all major systems. Massive jigs hold the pieces in perfect alignment during welding, ensuring that the combine stays structurally sound across thousands of hours of hard use. Paint booths supply multiple layers of corrosion-resistant coating and signature yellow paint to protect the body for years in the elements. Meanwhile, the body panels, including side shields, engine hoods, and grain tank hatches, are formed and painted separately for modular assembly later. At the heart of the CR11 sits the mighty FPT Cursor 16 engine. Producing a staggering 775 horsepower, it's one of the most powerful engines ever fitted to a harvester. It's lowered into the frame using hydraulic lifts and then connected to the driveline, hydraulic systems, and cooling units. Advanced hydrostatic transmissions are assembled next. These allow precise control over speed and torque in the field, even on inclines or muddy terrain. High-capacity cooling systems, turbochargers, and diesel exhaust fluid systems are added to maintain efficiency and comply with Tier 5 emission regulations. Once mounted, each engine undergoes a cold start test. Sensors monitor oil pressure, fuel delivery, and vibration levels to ensure every unit meets strict performance specs. Quick question for you. If you had to name this 775 horsepower beast, what would you call it? Drop your name idea in the comments below. We'll pin the most creative one. Did you know? The CR11's engine produces more horsepower than a NASCAR race car, while operating in mud, dust, and heat for 16 hours straight. Inside the CR11, twin 24-inch rotors, each the length of a small car, form the core of the threshing and separation system. These components are CNC machined from high-strength steel and balanced with sub-millimeter precision. The rotors spin at high speeds to thresh crops, rubbing the grain loose from the stalks. The machine then separates grain from husk using sieves and airflow. The CR11 includes New Holland's patented IntelliSense system, which constantly adjusts rotor speed, sieve openings, and fan pressure, automatically optimizing for every crop and terrain. Each rotor is mounted onto a heavy-duty bearing system, then connected to hydraulics and tested at high speed for vibration and balance. Why twin rotors, not one? Because two gives more surface area, better grain separation, and lets the CR11 harvest more than 130 tons per hour without choking. Next, the grain tank and auger system are installed. The CR11's tank can hold up to 20,000 liters, more than many small silos. The tank is built with sloped walls and vibration panels to ensure smooth, fast unloading. The unloading auger extends up to 8 meters and can discharge the entire tank in under 90 seconds. Engineers install high-torque hydraulic drives and flexible seals to allow operation at any angle or slope. Precision load sensors are calibrated to measure and log every kilogram of grain. A retractable camera system provides a full 360-degree view from the operator cab, and smart lights guide unloading at night or in low visibility. The cab is the brain of the combine. Fitted with a luxury seat, panoramic glass, and air suspension, the operator's station is more akin to a pilot's cockpit than a tractor. Ever wonder what it feels like to pilot a $1 million farm machine? With panoramic glass, climate control, and auto steer, it's basically a spaceship for soil. Technicians install a full suite of digital tools: a 12-inch IntelliView display, real-time GPS mapping and yield data, auto steering, grain loss monitors, and active seat suspension. Every wiring harness is color-coded and anchored to reduce vibration damage. Climate systems and sealed connectors are added to keep the cab comfortable and fully functional in extreme weather and rough terrain. Then comes the sensor suite. LiDAR modules, ultrasonic detectors, and HD cameras are mounted with laser alignment tools to ensure pinpoint accuracy. Specialized diagnostic ports are installed to allow real-time system checks and firmware updates. All components are tested individually before being linked to the central computer. Even a small error in one sensor can disrupt the entire automation system, so precision is everything. Parallel to the electronics phase, hydraulic systems are installed, arguably one of the most intricate stages of assembly. These systems control everything from rotor positioning and header tilt to unloading augers and ground drive mechanisms. How do you keep hydraulic lines from exploding under 5,000 psi of pressure? New Holland's answer: digital torque wrenches and double seal couplings. High-pressure steel tubing and reinforced hoses are cut to length, bent using computer-guided presses, and fitted with double seal couplings. Each hose assembly is flushed with fluid to remove contaminants before installation. Digital wrenches tighten every valve with extreme precision, just enough to seal the system, without risking even hairline cracks. Hydraulic fluid reservoirs are installed and connected to return loops. Then the system is pressure tested using nitrogen and oil, simulating extreme field conditions. If one valve leaks or responds too slowly, it can throw off the entire combine's balance. That's why each system is tuned like a race car, down to the millisecond. The CR11 isn't a one-size-fits-all machine. It's modular, adaptable, and can be customized for virtually any crop across any continent. That flexibility starts at the very front, the header. This is the attachment that cuts and gathers crops before they enter the feeder system, and it plays a huge role in harvesting efficiency. New Holland offers a range of high-performance headers to pair with the CR11. For wheat or barley, a draper header with a flexible knife and conveyor belt ensures uniform feeding, even over uneven terrain. For soybeans, a flex auger header allows the blade to contour to the field. For corn, specialized chopping headers slice stalks, strip ears, and leave behind manageable residue, all in one motion. Each header is connected via the feeder house, a powerful belt and chain system that elevates the crop material into the rotors. Before shipping, each CR11 is matched with a header type, depending on the region and crop focus. This modularity makes it a global powerhouse, equally effective in North American wheat belts and South American soybean farms. Once the engine, rotors, cab, and grain systems are complete, the combine enters the final assembly. Technicians add tires or tracks, lights, guards, stairs, and decals. All hydraulic lines are pressure tested, fluids are topped off, electrical systems are scanned, then comes calibration. Each system is tested under load using simulated crop material. Rotor balance, fan speed, header tilt, steering response, and GPS alignment are dialed in. A test driver then takes the machine for a field simulation, verifying stability, vibration levels, power delivery, and yield reporting. The machine must perform flawlessly in 10+ harvest simulations before it earns final certification. From CAD models and robotic welders to twin rotors and cloud-connected sensors, the New Holland CR11 is truly a marvel of modern engineering. Every grain it collects is a product of design precision, mechanical genius, and digital innovation. If this deep dive sparked your curiosity, hit that subscribe button for more epic engineering breakdowns. Which part of this beast impressed you most, the twin rotors or the engine? Let us know below. Until next time, keep exploring the machines that feed the world.